All right, in the last video, I showed you how we can use this program from Grasshopper that we created, where the robot simply moves from point 1 to point 2 to point 3, and actually send it to a real robot, or in our case, it was a UR sim. Just to show you again, we use the remote connection, set the IP address of the robot, and then when we hit this button, the robot immediately starts moving. Keep in mind that if you are connected to a real robot, it doesn't matter if you're in the same room or if you're on the other side of a campus or a company, the robot will still start moving. So make sure that you actually know which robot you're connected to, that the IP address is correct, and if you are in doubt, you should always disconnect your computer from the network or disable this Grasshopper component to make sure that you're not accidentally sending commands to the robot if someone else might be working with it, or you haven't refined kind of the coordinates and positions and the robot might break something. So in following videos, I will also show you how we can actually add a safety feature. So a quick pop-up that will come up on the robot pendant, and the robot will not move until the pop-up is pressed at the robot. So for now, I will show you in this video more ways of defining our robot program, and especially of the creating a robot target. We've already seen the configuration input that we can press to define in what way the robot will access a certain point. So this is not the orientation. The orientation the robot has at its tool stays the same. However, the way the joints are configured changes. You can, of course, imagine yourself. You can grab something with your elbow down, or you can grab the exact same thing with your elbow up, and this is also something that the robot can do, of course. We have this next input, which is the type of motion. And in this case, this is a joint motion. If you don't know the difference between joint and linear motions, this is something that is very basic to any kind of robot programming. I will show you very quickly in the UR sim. If you know this already, then you can skip this part. But for anyone who doesn't know, this would be very important to know the difference between move J, the joint move, and move L, the linear move. I have a robot program here with 3 waypoints. And these waypoints, as you can see right now, are under a move L command, and they are perfectly straight. The lines or the motion path between each waypoint is a straight line. However, I can change this to a move J, and now we can see that instead of it being straight lines, each part is now kind of this arc, so it's a curve. And you might wonder, if you've never seen this, why would the robot move in a curve between 2 points? Just let me kind of simplify it without going into too much of the detail why that is. It's much easier for the robot to actually move in this arc motion than to move in a linear motion. If it moves in an arc motion, it needs to kind of have much less control over each of its axes, and can also be much quicker to reach certain points. We also don't get into singularities as easily as with linear motions. If you don't know what a singularity is, don't worry about it for now. You will probably find out sooner than you would like. So back to Grasshopper. We have created this target, and then we can set if we want a joint motion or a linear motion. Now, to kind of check this out in Grasshopper, we can also have our program simulation, and we use a component under the utility, which is simply called a simple trail. And we use the program output from the program simulation component. And when we then go to the start and iterate through our points, we can then see this trail, which is now highlighted in green, between the different points. And as you can see, right now we are in linear space, we're using a linear motion, and this is completely straight. If we use a joint motion, and go back to the start, then you can also see here, it might not be super obvious, but there is a curve to this motion. Let me try to maybe change the position of these coordinates in such a way that this is much more pronounced. Now you can see it a bit better, how the robot moves in an arc motion. That is the motion type. If you're already familiar with programming robots, you know when to use which motion type. If you're not familiar, usually you would use the linear motion type, simply because we can control the motion of the robot much more precise. The robot doesn't deviate from a course that we give it. So for all motions that we want to tightly control, so if we're extruding something, if we're actually putting something in a very specified position, then we would use a linear motion. But if we have a motion where the robot simply, for example, resets or goes to a neutral position, then we can also use a joint motion. The next input is the tool input. I will show you the tool input in a following video, because this is also, of course, very important. We can set the speed of the robot, and for that we should use a speed parameter, and we should also use a create speed component. And here we can then basically set our speeds. As far as I'm concerned, this is in millimeters per second, and here we can set the speed of the robot, which is of course very important for creating programs and also controlling the robot. We might want to have some targets that are approached very quickly, others that are approached more slowly. We have more inputs, for example, the zone input, we have the command input, we have a frame input, and we have an external input. Most of these you don't use all the time, but I will go through them anyways. The zone input is the basically what is called the blend radius in universal robot programming. So right here, for example, we have these waypoints, but as the robot moves from one waypoint to the other, it actually stops at each waypoint before moving to the next. And we can use blend radii. For example, in this case, I just added a blend radius of 50 millimeters to this to these waypoints, and then I can see in the graphics tab that instead of moving to one point, stopping before changing direction and going to the next point, the robot actually has a smooth motion and has this, basically a fillet, this rounded corner to all of its motions. This is different from linear motion and joint motion. This is a blend radius, which is called a zone in the robot's program. To create a zone, we can simply add the zone parameter, and then, for example, have a zone of 50 millimeters here. I'm actually not sure if or let's maybe crank it up to even 100 so we can actually see it. I'm not sure if the simulation will actually show this, but let's check it out. No, so the simulation does not necessarily show this blend radius, but trust me, it's there. It is then sent to the robot. You can actually see it here, where we have the zone 1 that has a certain value. So this is the blend radius. Then we have a robot command. So this would basically be a special robot command that we can set, that is then executed by the robot before each of the targets. For example, we could say, hey, before you approach this target, you set, for example, a digital output to a certain value, or we can send something to the log. How to do this will be discussed in a different video, but for now you just know that if you want to do something special with the robot, with the inputs and outputs, you can use the robot command input. Then we have the frame input, and this is basically so that we can use the same thing, the same target, but maybe have it in relation to a different position. So we have the same target or the same list of targets, but one is, for example, in relation to the base, so the XYZ 0 coordinates here, and another one is in relation to an offset of these points. Something that you don't really use that often, depending on what you're doing, but just know that if you want to kind of shift a whole list of points or certain targets, then you can use the frame. And the last one is an external axis. So it would be possible to put the robot actually on an external axis and actually move the entire robot to have more range of motion, or to have for example, a rotational axis or something else that is also controlled. So we can also kind of define what this external axis should be doing whenever this target is executed. So that should be it for now. I hope you have a better understanding now of the create target component. If some of which was maybe confusing, you shouldn't be too afraid. There will be repetitions of this in the following videos whenever we use a certain input. I will explain it in more detail, and it will also become much more clear once we actually get to specific examples.